Here you see a capacitor with a capacitance of 1000 microfarads and a maximum safe operating voltage of 50 volts. Here's a smaller capacitor with a capacitance of 10 microfarads and a maximum safe operating voltage of 35 volts. Capacitors come in different shapes and sizes, as you can see. The one thing they all have in common is they're constructed in one way or another of two conducting materials separated by an insulator. Now, the simplest version of this is something we refer to as a PPC, for parallel plate capacitor. Sometimes a parallel plate capacitor could just be filled with an insulator as simple as air. So then we'd have an air-filled parallel plate capacitor. The plates are separated by some distance d, and each plate has a surface area of A. What these capacitors do when connected to a source of electric potential difference, let's say that terminal connected to the positive of a battery, and this wire connected to the negative terminal of the battery, then the battery provides a potential difference that can remove electrons off of this top plate and deposit them onto the bottom plate. So now the top plate is lacking in those electrons, it's positive, and the bottom plate is negative. Some people say that capacitors store charge because the top plate stores positive charge and the bottom plate stores an equivalent magnitude of negative charge. But as a system on the whole, the capacitor stores no charge at all. What a capacitor really stores is energy. Those charges would like nothing more than to recombine and neutralize, and in doing so, an electrical current can provide energy. You see these capacitors on integrated circuit boards. Take apart a computer or any modern electronic device and you'll most likely be able to find some capacitors on the printed circuit board. One example of that is on the circuit board in a disposable camera, where the capacitor provides the stored energy to allow the flash to go off when it's time to take the picture. So let's define a quantity known as capacitance. Capacitance, by definition, is equal to the amount of positive charge stored on the positive plate in comparison to the potential difference that was used to produce that electrical charge. So again, if we refer to the parallel plate version of a capacitor, if no potential difference is presented, then each charge, or each plate, I should say, has neutral charge. But when connected to a battery or some other source of potential difference, aka voltage, like we say, if this is a positive and that's a negative terminal, then this plate will be positively charged due to a lack of electrons. This plate will be negatively charged due to excess electrons. The amount of positive charge on the positive plate, or if you want, the magnitude of the negative charge on the negative plate, is represented by the Q in this equation. It might be best to write this equation in this triangle form. We've seen this before. For example, F equals MA. In this case, we'll make a triangle for charge is equal to capacitance multiplied by voltage. So the amount of charge on a capacitor is equal to the product of the capacitance and the voltage used. In other words, if you see two different capacitors, one's very large, we can take like the example from above, this one's maybe 1000 microfarads, and you have another one that's smaller, let's say this one's only 10 microfarads, and the question is, which one holds more charge? Well, that's a bit misleading. Let me write down two questions. Which holds more charge, or which is capable of holding more charge? Two different questions, right? The one that holds more charge, well, that depends on two things. Not only the amount of capacitance, but the amount of voltage. So it could very well be that the smaller one's the one that holds more charge if a much larger voltage was applied. So let's say delta V for the smaller capacitor is really large. So a large delta V and a small capacitance could actually produce the same amount of stored charge as a small delta V and a large capacitance. You get the idea. So it's not really practical to ask which holds more charge. What we're really interested in here is which has the greater capability of holding charge, and that's what we mean by capacitance. And if capacitance is indeed the ratio of charge in comparison to the voltage required to produce that stored charge, then the units for capacitance must be coulombs per volt. And we give a special name to that. We say a coulomb per volt is a farad. Let's write that out. 1 farad, a 1 farad capacitor will store 1 coulomb of positive charge on its positive plate when 1 volt of electric potential difference is applied across the two conducting plates. A farad is a very large unit of measurement, so it's typical that you'll see microfarads, maybe even picofarads or millifarads. So as you know, micro means 10 to the negative 6th, pico is 10 to the negative 12th, milli is 10 to the negative 3rd, and that's it. When you think capacitance, think of this ratio.